In this tutorial, I will give you an introduction to SMAK and provide an overview of its functions. First, let's open a file by pressing the big yellow Open button. So I'm going to select this file to open, and now it loads. In the newest version of SMAK, that's SMAK 2.0, you can open multiple data files at once. So all you need to do to open another data file is click Open again, and then scroll over and click the one that you want, hit Open, and it brings up a new tab with this new file. You can do that many times, load up multiple files. Let's try one more. You see it opens up a third. If I decide I don't want to work with all of these files, I can just go ahead and go File, Close File, and it's going to close whatever tab is highlighted. Okay. So under Data Channels, you can see all of the elements that you collected at the beamline. I'm going to select calcium, and now you can see the display of the calcium intensity across your entire map. So the dark blue pixels are areas where you have low intensity, and the red pixels are areas where you have high intensity. If you don't like this color scheme, you can go down here to Color Maps and change it. So there's a number of ones available. You could, for instance, select grays. I prefer jet. That's usually what I stick with. You can change the contrast on this display using the sliders for low and high on the right-hand side. So you can see as I decrease the high limit, I can see more and more of my particles, and I saturate more and more pixels. I can also click Log Scale, and that will show me the log of the intensity of every single pixel. I can also invert the color scheme if I like. As you see, as I'm scrolling around and moving my mouse, the coordinates, the red coordinates at the bottom of the screen, are constantly updating. These coordinates are X, the horizontal position of the pixel, Y, the vertical position of the cursor, and Z, the counts on the detector. So if I go and sit on this red dot, you can see that this pixel is at 6.18 millimeters, 1.54 millimeters, and has 1460 counts. So finally, you'll notice that this box actually doesn't have a scale bar on it, so we don't know how big this is, what the dimensions are. In order to get the scale bar, simply go to Legend, and you're actually going to go ahead and show the scale bar, and now it automatically puts it on the map. It always uses microns, so this is a 400 micron scale bar. There are four major data analysis procedures that we'll cover in this tutorial, and these are accessed by the four large buttons on the SMAK screen here. So this is correlation plots, tricolor plots, map math, and PCA analysis. However, before we do any of these analyses, there are two data processing steps that I almost always do. So the first step is to right-click on the display and scroll down to Edge Removal. Edge Removal will remove a single pixel from the entire perimeter of the map. And so each time you click Edge Removal, it removes a 1-pixel perimeter. Often there is a line of dead pixels on the left-hand side of the image, and this arises from a quirk in the way that we collect data at the beamlines. When you do this, you'll see that the image will automatically rescale, or the contrast in the image will automatically rescale. That was a little bit hard to see for this image, but if we go over to the next tab and then do that again, you can see that we definitely had a bad line of pixels, because now that we've removed them, all of these calcium particles really pop out at us. The second image processing step that I usually do is I usually blur the pixel intensities. This process averages each pixel intensity by the intensity of the surrounding pixels, and this has the effect of reducing noise at the expense of blurring the features slightly. So to do this, we're going to go to Process, and we're going to select Advanced Filtering. There are a few different algorithms that you can use for doing this averaging. We recommend people use blur. You can then select the filter size. The filter size controls how many pixels you're averaging over. We typically set this at about 5. And then there's also this blur standard deviation. We're not exactly averaging adjacent pixels, we're actually applying a Gaussian distribution function. And so this standard deviation applies to that Gaussian distribution function. So I like to set that at about 0.8. That's what I'll stick with. And now you simply want to apply this to all of the channels that you're interested in. In this map, I'm interested in calcium, I'm interested in potassium, and I'm interested in silicon, so I'm control and left clicking on these to highlight them. And then I'm going to click Save and Done. And now if I scroll down to the bottom of my data channel list, I'll see these new channels were created. Let's go ahead and do that for this as well. So process, advanced filtering, blur, filter size of 5, standard deviation of 0.8, and select calcium, potassium, and silicon. Save, and then click Done. Okay. In addition to these two data processing steps, it may sometimes be necessary to normalize the data channel by either the time channel or by the ion chamber upstream of the sample. Note that these steps should be taken before you do any blurring. So when do you want to do this? Well, if you see periodic vertical striping in your image, you likely need to normalize your data by the time channel, which provides a record of when the detector data was recorded. So let's look at the time channel quickly. You can see that it consists of a pattern of vertical striped lines. So if you see this pattern reflected in one of your data channels or one of the elements that you're interested in, that means that you need to normalize by the time channel. To do this, simply click Map Math. This brings up a new window, and let's pretend that was a problem for my calcium. So I'd select calcium, I would then select the operation to be divide, and I would divide the calcium by the time channel. And I would give it a new name, something like calcium time, and I would do the calculation and save the calculation. When I go down here, I have a new channel called calcium time. In this example, it was not necessary to do that. The calcium channel is fine. Occasionally, you may observe variation in the incident flux at the beamline that causes noticeable variation in your fluorescent intensity. This is pretty rare, but in this case, you may want to normalize your fluorescent channel by the incident flux. In this case, the incident flux at beamline 14.3, which is where this data was collected, is I1. So I would go down here and select I1 stream. So now you can see that I'm taking the calcium channel and I'm dividing it by I1. And I would give this another name, something like I1 norm. Do the calculation, save the calculation, scroll down, and you can see your new channel here. So remember to treat all your channels the same. If you do this for one channel, it's a good idea to just do this for everything. However, don't get hung up on normalizing all of your fluorescent channels to I1 or I0 if you don't have to. When you're analyzing your data, it's okay simply to use the raw fluorescent channels without any normalization. If you want to be quantitative, that is, if you want to convert your data from counts into mass per area, you will take into account the incident flux during this procedure, and this is covered in another SMAK tutorial that deals specifically with quantification. Finally, it's a handy thing to know how to remove channels that you don't need. So in this instance, calcium time and calcium norm, those channels, we actually didn't need to adjust our calcium data at all, so I'm going to go ahead and get rid of them. So for that, I go to File, and I'm going to go ahead and remove multiple channels. This brings up a window. I can scroll down, and I can simply highlight both and click OK. Great. Okay, And finally, as you're processing your data, it's a good idea to save it periodically. So when you save your processed data, it will save any new data channels that you've created in this window here. I've generated 3 channels already, so it's probably a good time to go ahead, click File, and Save Data, and it'll automatically append the word process onto the name of your data set. Of course, you can change that if you like, and then you can save. So let's now go over some of the analysis functions in SMAK. We'll start with tricolor plots, and these allow you to plot up to 3 channels at once, overlaying them in different colors. I'm going to go down. So this is your red channel, your green channel, your blue channel. You have the channel name here, and then the low limit, which is automatically 0, and the high limit is read automatically from the plot. So this is the highest intensity that you have for that particular channel. I want to look at my blurred channels, so I'll scroll down. I'll make calcium red, potassium green, and silicon blue. And now I've come up with this nice tricolor plot. Okay. It may often be the case that you can't see one or the other colors very well, and so you'll then want to adjust the limits in order to enhance the contrast. So for instance, let's say I couldn't see calcium very well. I might set its limit to be 25 to 50% or so of the maximum value that you see here. So if it's 1340, 15% of that, or sorry, 50% of that is, I'm not doing very good math here, but it's around 680 counts or so. So just write that, then hit enter, and you can see that it rescales. So now these bright calcium spots are saturated, and you can see that there's calcium in the background. I actually don't like this very much, so I'm going to go to limits, and there's an option to restore defaults that will put it back to the original. So the colors in the red, green, blue plot, and the reason that you can only plot up to 3 at once is because these 3 colors mix in a quantitative fashion. So you can actually judge the relative amounts of calcium, potassium, and silicon by looking at the exact color. To see a legend for the color, you can go up to legend, and it will allow you to view the legend, which is shown here. So you can see that bright red is entirely calcium, bright green entirely potassium, and bright blue is entirely silicon. Notice though that there's a lot of pinky orange in here, so that probably falls around here. And so these pinky orange particles are actually a mixture of calcium and potassium. And then finally, you can of course save the tricolor display under either this file window or on your tricolor plot control panel. You can also save it under this file window. Okay, so let's move this out of the way for a minute. And next, we're going to go ahead and look at correlation. So I'm going to press correlation plots, and this brings up a new window called correlation plotter. So the correlation plotter allows you to plot the intensity of, say, the calcium pixels versus this silicon intensity in all your pixels. So each dot on this plot represents a different pixel, and so really you're just taking the silicon intensity of that pixel and plotting it versus the calcium intensity of that pixel. So you can do many things with the correlation plots. These are really helpful ways to look at your data. For instance, right away I look at this and I see that I have roughly 2 populations of calcium and silica in this map. I have a population of pixels that are high in calcium intensity and low in silicon intensity, and I have a population of pixels that's high in silicon and low in calcium. So I may think these are actually 2 different types of materials. So let's say I actually want to figure out which pixels in the image, the pixels on the correlate, or the points on the correlation plotter correspond to. there's a way to do that, and it's called masking. So to mask a point, or to mask a set of points, we're going to define the mask, and then we're just going to left click to draw a lasso around these points. So I'm going to say that I think is one population. To end this lasso, I'm going to double click. Okay, now I can go ahead and use the mask, and now I see that all of the pixels that aren't inside of my lasso are completely blocked out, and I can only see pixels that are inside of my lasso. So now if I go and click on my silicon window, I can see that those pixels correspond to these dark red hotspot areas. So ignore the mask, use the mask, ignore the mask. You can see that I'm selecting the bright silicon areas. You can also clear the mask by going down here and setting clear. Okay, so you can actually also mask an area on the image directly and then view the mask points in the correlation plot. So let's say I wanted to look at this silicon particle right here. What I would do is I would shift and left click, and then I would just draw a little shape around this, double clicking to close. When I double click, it brings up this window here, and I say make a mask out of that shape. Click OK. Now you see I've masked off that area. Now if I come over to the correlation plotter, I hit color and then go to color theme, I can say highlight mask, and it will show all of the points that are part of that cluster that I made. Let's see, ignore mask. Okay. Also, if you wanted to select, another way to select a region of the plot to show in the correlation plotter, a region of the display to show in the correlation plotter, is to zoom in on an area. So let's say I want to see all of these particles and what they look like on the display. What I would do is I would control left click and drag, and now I'm zoomed in on that area. Notice when I zoom in, the Tricolor image display, which I had left open, that also changes its dimensions, and then the correlation plotter will also update. So if you want to get rid of the zoom, you go clear zoom, and you can see the clear zoom actually removes your edge removal, so you need to go ahead and do that again. 1, 2. So let's just see that one more time. Control, draw box, you're only showing that one particle, and you can see the correlation plotter and the Tricolor image display have rescaled. Let's go ahead and do do clear zoom and edge removal again. Okay. So next, let's say you actually want to look at not only this data file, so this L2 data file right here, but let's say you also want to know what's going on with this data file here. You want to compare what the calcium to silicon correlation looks like for both of these images at the same time. There's actually a way to do that. You can go to color, color theme, click on Multifile, and now the green dots are whatever tab is currently selected. So in that case, this is the L2 tab. And the blue color is whichever tab is not selected. Okay, if we want to get rid of it, let's just put this on none. Finally, another thing you can do with these plots is you can do regression analysis. So let's say I want to actually fit a regression line through this data. I can go to analysis and hit regression, and it's going to plot a line. It'll give me the slope, the intercept, and the Pearson correlation coefficient down at the bottom of the screen. This isn't very good because actually there are two distinct populations here. So we can actually, instead of doing regression, we can try a multi-regression where we can use multiple lines to try to fit our data. So let's try fitting this with 3 lines. Hit OK, and now it's going to prompt us to put in starting guesses for the slopes. It gives us default values which we can keep, or we can try changing them. So I'm going to try maybe 0.01 for this. I'll leave this at the default, and I'm going to put in 0.8 for this, see if I can get any traction. It's fitting the correlations. Okay, and those are the 3 regression lines that it came up with, so, you know, maybe not such a good job, but if I try fitting maybe 1 or 2 more regression lines, I might be able to get a better fit through here or a better fit through here. It really depends on the correlation, how well this analysis works. The slopes of these lines are given down at the bottom of the plot here, so you can see the M1, M2, and M3 slopes that it predicted. Okay, if you want to get rid of these lines, you can actually just click off of that channel and then click it back again, and it'll update the plotter. You can export this data, so you can bring it into another plotting program and plot it up according to whatever way you want to present it. To do that, you would go File, and you would go Export the data. So there's one more thing that I want to show you how to do in the correlation plotter. But first we're going to go and look at this other analysis tool we have first, PCA. And then we're going to use that to feed back into our correlation analysis. There are actually 2 other tutorials which provide an in-depth explanation of these statistical tools. So we're only going to go very briefly here over how to use one of these analyses. And before we do this analysis, I actually want to make a new channel. In these 2 samples, the 2 samples that I have open, what I actually am really interested in is the ratio of calcium to silica. So I want to know if there are particles that are different than one another in terms of their silica and calcium contents. So to help me see this, I'm actually going to go to Map Math, so I can just bring this window to the fore, and I'm going to make a new channel that's calcium divided by silica, and then I'm literally just going to divide it by my silica channel. I'm going to do the calculation and save the calculation. Okay, now you can scroll down, see I have that new channel. And now I have a new plot where you can see these dark blue areas. Those are areas with a really low calcium to silica ratio, so those were the high silica particles. And then I have some other areas that have really high calcium to silica ratios. So now let's go back and select our PCA analysis button. This brings up a new window here where we can select the channel that we want to work with, and then we can apply a whole number of different clustering and other statistical tools to these different channels. The one that we're going to use now is called Kmeans, and this is a clustering analysis tool. And this clustering analysis tool basically groups pixels in your sample according to their signal. So since I'm using a channel that's the calcium to silica ratio, I'm going to have pixels that are grouped based on their calcium to silica ratio. When I click on Kmeans, it asks me for the number of clusters, and I'm going to tell it 4. So a cluster is a group. When I say that I want 4 clusters, what I'm saying is SMAK, make 4 different groups of pixels and put pixels into that group depending on their calcium to silica ratio. So I'm going to have one group that's really high calcium to silica, one group that's really low calcium to silica, and then I'll have 2 groups that have some intermediate calcium to silica ratio. So click OK, scroll down, and I have a new channel. It's called Kmeans Clusters 1. And now you see that I have color-coded all of the pixels that are present in the map, and they're color-coded to that calcium to silica ratio. So all of the red pixels have a similar calcium to silica ratio, which is different than all of the yellow pixels, which is different than all of the light blue pixels, which is different than all of the dark blue pixels. Now let's go back to our correlation plotter, and I actually want to go to color. I want to go to color theme, and I'm going to hit cluster. And when I do this, it's going to show me the location on the correlation plotter of all the pixels that fall into the dark blue cluster, all of the yellow cluster, all of the light blue cluster, and all of the red cluster. So I can go back to my map and I can see, okay, well, certainly I expected that all of my high calcium, low silica pixels would be in these regions where I remember seeing really high calcium intensity. And in fact, if we go over to the data channels, I'm going to right-click calcium blur. And when I right-click calcium blur, that brings up a new display for me. And I'm going to edge removal quick, twice. Great. And now I can see, like, yeah, that blue area, that's a really high calcium area right there. If I look at the red, that's really high silicon, and that showed up right here and right here, and I remember those were really high silicon areas. But then also, you know, I have background on this sample where the silicon intensity is much higher than the calcium intensity, even though both intensities are very low, and so those are being grouped together with these particles that exhibit a very high silicon intensity. So that's a really nice feature, to be able to start to group and classify pixel intensities in your displays. So at this point, we've covered a number of the basic functions that you can perform in SMAK. There are many other functions in SMAK, and we will cover a lot of these in other tutorials. So quantifying, that is determining your mass per area instead of your intensities, Zane's fitting, the statistical tools, which I just touched on today, and then also we can do particle and masked statistics. All of those will be covered in separate tutorials. There are some processing tools that we won't cover in these tutorials, such as registering images that are misaligned. You can also change image resolution. There's a handful of other things you can do, and these are all covered on our website. So finally, I'll end this tutorial by reminding you that it's always a good idea to go ahead and save your data, which is going to save all of your newly created data channels. And you can also save your display, you can save your Tricolor display, and you can export some of your data as well here.